All right. So today we are one more time moving on to new areas that we haven't seen before. This time it is something that we call observers, right? Something that we call observers. I would motivate it in just a second. I would explain what it is, motivate it, and so on. But just as usual, let me remind you that what we were able to do last few lectures was to go to what we call optimal control. Optimal control, that was the idea that you could find somehow the best possible controller for your system, right? We defined in which sense it was the best possible control in terms of a cost function, right? So in a sense, we obtained an instrument to tune the controller gains. You remember in the very beginning of the course, we started by saying, okay, we have a stability, which is a desirable property. Then we have a controller, which allows us to obtain this stability. And now, last lecture, we obtained an optimal, you can say, the best way to tune this controller. So it feels as if the whole circle was completed, right? Well, today I will show you one sense in which the circle was not completed yet. Yeah. And we will take advantage of the material of the previous lecture to do work here. All right, let's begin. Let's begin. So previously we looked at the systems such as the one I present here. We say, okay, we have a state. Derivative of the state is equal to matrix times the state plus a matrix times control input, right? X dot equals to AX plus BU. And the controller that we considered would be a linear controller. U equals to KX. You remember from the last lecture, we more or less proved that this is actually the optimal control form for this type of system, right? We showed that it comes from the conditions of optimality, right? When we solved the Riccati equation, the controller we obtained was a linear controller. Okay, so this was quite interesting, and now that we know that optimal control has this form, we feel even more confident about considering this type of systems, right? Linear system, linear control, great. Okay. There is one problem though that we have not yet answered, and that is, in order to implement this in practice, in order to find such U, which would be equal to a matrix times X, we actually need to know X. It is not sufficient to just know which control gain to choose, right? K, you remember this matrix. We discussed in the last lecture how to choose it in the best possible way. It was this multiplication of three matrices, right? R inverse, B transpose, S, right? From Riccati equation comes. So we understand how to choose K. That is not a big problem anymore. But how do you know X? X is your state variables. So for example, if you have a spring mass damper, it might be your position and your velocity. If it is a DC motor, it might be your current and your angular velocity. Or if you do position control on your DC motor, it can be your position, your angular velocity, and your current, right? So all three. Okay. So question is, how do you know X? How do you know X, right? That is a good question. That's a good question. Okay, let us try to start answering it. And to start answering it, I think what we could do is we could imagine that this information comes from measurement, right? That we directly measure it. Or as we will see in a little bit later part of the lecture, we can say that we estimate it, right? Right, but let's for now just stick to measurement. So we measure it. Okay, so we have a sensor. It measures our position, measures our velocity, measures our torque, our current. Sounds very good. Unfortunately, it is not so easy in real life as it is said. So let us consider just some problems with this proposition. So some problems. So first of all, we do not always have sufficient sensors to measure everything. While it is quite realistic to try to measure, for example, position of a motor, that is a very typical measurement that is often done. Direct measurements of the velocity is not typical, but we can get over it by differentiating position measurements. So, sometimes it is possible, and maybe indirectly, but it is possible, right? Currents, some motors allow you to measure current. Again, it is done indirectly by measuring voltages, but more or less it is possible. All right, good enough. But there are situations in which you simply don't have measurements that you want. For example, for a quadrotor, let's say a drone flying somewhere doing photography, the height you can measure only very imprecisely, if at all, right? You may not have a sensor for height, right? Some drones would have a distance measurement that is used simply when you land, and often that is all information about the height that you have. Or alternatively, your absolute position. You can do it with GPS, but if you are indoors, your GPS may not work. So you may not have any measurements for your position. Orientation can be done with a magnetic compass, but not always is possible again, especially if you are indoors with a lot of metal around you. So often enough, you simply don't have a direct way to measure something. Okay, all right. And even if you have all of those, you can imagine, for example, vertical acceleration of your quadrotor, almost impossible to measure. Like there are no direct measurements for that. So is not easy. Is not easy. But that is, of course, not everything. Here, I will just survey very quickly other sources of problems. For example, let's say you have like your measurements can be done digitally, which is very typical, right? You have a sensor which works like as a digital system. So it's done at discrete time intervals, not continuous stream of measurements, but a discrete sequence of measurements. Also, measurements can be disrupted. Something can go wrong, and you will just not receive a measurement in time. There could be unmodeled kinematics or dynamics. For example, let's say you build a robot, like you yourself build a robot in a lab, but it is kind of bendy. Like you think you have a link which is straight, and you measure its position, expecting to know where the tip is, right? But the link you built is made of thin aluminum profile, so it kind of bends a little bit, right? And your motor, you have a motor here. The motor, you would think it is like if it sits in this position, the link is horizontal. But what actually happens, you have a backlash. So the motor actually allows the link to go like this a little bit, right? You have a backlash. And you have maybe a few other problems like this. So in the end, you measure something, but it doesn't correspond to reality. Like it doesn't give you information about objective reality. Like you don't have enough states basically in the system, right? Possible, especially for home-cooked robots. Right. Your sensors can be imprecise, non-linear, biased. So your sensor can simply lie to you, right? And you can have other physical effects. At the end of the day, measurements are almost by definition imprecise. Like it is almost a physical fact that you cannot produce infinitely precise measurements, right? You can only measure something with a finite precision. Okay, so that is a problem. That is a problem. All right. So that is what we said about the uh, situation with the measurements. So the conclusions I want to make from it is that you cannot simply expect to be able to measure whatever you need to have measured. Often enough, what happens is you want some information, some part of X, but it is simply not directly available to you. So that might be an issue. Okay. Now we can like with this in mind, we can introduce a new type of idea, right, for our control. Since we don't have X, we cannot really do control in the sense of U equals to KX. This is not possible. So instead, what we want to do is to base our control on something else, not on X. Here is how we can try to do it. So we still have our dynamics. It is the same, right? Dynamics in general does not depend on what we want or how we control. It is just there. So x dot equals to ax plus b. Right? We still have we have our measurements. If you remember, we discussed this part earlier. Let me point it out now. Y equals to cx. What is this? Well, in the lecture, probably in the lecture number 1 and lecture maybe number 3 or something, we talked about it in terms of like a variable we care about, right? We said that y can be the same variable as we use in OD and so on. Right, all this is true. But here for today, we have a very concrete interpretation of what y is. Y here is a measurement. That is what you measure, right? So here, y equals to cx is what you measure. So your sensors basically transform your vector of states x into a vector of some variables y. Specifically, just as an example, it can look like this. y1 is equal to, let's say, x1. y2 is equal to x5. Let's say y3 is equal to x6, for example. Right? So it means that x number 2, x number 3, x number 4 are not measured at all. You only measure x1, x5, x6, for example. Can be more complicated than this, of course, but it is very typical when y and x correspond in this fashion, where a component of y is just one of the x's. So in this case, the matrix C would obviously be something like this. It would be C equal to 1, 0, 0, 0, 0, 0, right? And it would be 0, 0, 0, 0, 1, 0, and it would be finally 0, 0, 0, 0, 0, 1. Right? So this, in this case, in this particular scenarios they presented, this is how it's going to look like. The C matrix will be just this collection of rows with a single number 1 in each row. Right? Doesn't have to be this way, but it is very typical. It's very typical. Why is this typical? Is because often the way you present your state has a physical meaning. Your state is one of the angles you care about, or one of the velocities you care about. And often what you care about, you try to measure directly. So often your y measures directly this very state. That is why C matrix tends to have this form. But of course, sometimes you measure something indirectly. And in this case, C matrix would be more complicated. All right. So that is this equation, y equals to cx. Now, one more innovation. Now, what we do is we say, let us assume we have an estimate of x. So x, let us assume, is available to us as an estimate. So this x hat is not x, it's just a value which we hope is close enough to x. And we estimate it based on the history of outputs y. So we have y at each point of time as a function of x. And we use this y, but not just one y, like the whole history of y's, to estimate x as best as we can. Well, that is the idea. That is it. And then finally, the final innovation is now our u would be same, we have same control law, but now it is linear with respect to the estimate. The estimate. So our control law u is a function of the estimate of x. And the estimate of x is a function of all history of readings of y, where y is measured components of the state x. Does this make sense so far? If you have questions, so this is a good time to pause and ask.
I have a question. Why in y equal to c times x, we're using x, not x hat?
Okay, good. Let us try to address this point. So the question, if I understand the question, correct me if I didn't understand it. Why in this equation we have x on the right-hand side instead of x hat, right?
Yes.
Yeah. So okay, let me try to explain this. So this part, right, is the actual dynamics of the robot that sits in the physical world. So let's say it is our quadrotor. So this is the dynamic of our quadrotor. Okay. It actually describes how velocities of the quadrotor change with time, position of the quadrotor change with time. Okay. This x is actual collection of velocities and positions of this quadrotor. So we take these velocities and positions, we pass them through the measurement system, right? Through the sensors. And we get readings on those actual positions and velocities of this quadrotor. So same, but in other words, y has to do with the physical realities that we have in the world, but through measurement, right? So for example, we have a GPS, y would contain the readings of the GPS sensor. X is just a collection of all states of the drone, right? All positions, all orientations, angular velocity, absolute velocity, etc. All of this, right? Why would contain only the stuff that we measured with the sensors? So, for example, position, x, y, that we get from GPS, and orientations that we get from inertial measurement unit, right? So only some of the states, but they're still the same states that exist in the real world. Okay, so that is sort of, I can say, why we have X here as opposed to, for example, something else. But let us understand a little bit better what this is, right? This is not something that happens in the real world. That is something that we store in the memory of our controller. So for example, if we have Arduino on top of our drone or Raspberry Pi, for example, it will be stored in the memory of this microcontroller, right? Somewhere inside there will be stored a value, x hat. It's just a number, just a variable, right? And this variable will be updated as time goes on using new and new and new measurements y. So somewhere inside this controller, right, there will be this number. It will be updated over time, but it doesn't exist in the real world. So while this is just a description of the real world, this is a description of the measurements, again, in the real world. But this value y can be directly sent into our controller, into our Raspberry Pi, right? We can directly send it there using a protocol. You know, we can read it from the ports of the microcontroller. And now with all of this, so let me one more time see, like this exists in the real world. With all of this, we can now have a different part, like, you know, this and this, which can happen inside the microcontroller, right? So what I showed in orange here is stuff that is not really available to our microcontroller because it's just stuff in the world which we don't have any way to get from there. But what I showed in blue is stuff that directly available to the microcontroller because it is like y is being directly measured, transformed into a number, sent through the protocol directly to the port of our Arduino or Raspberry Pi. And this stuff in blue is computed inside the controller. So this is the dichotomy. And just to continue this, sorry, this part here is also computed inside the controller, right? And then the output, resulting output U, is going to, again, affect the physical world. It's going to be generated as a voltage, most likely, and is going to directly affect how the drone flies. Did this answer the question somewhat?
Yes, thank you.
Sorry, but now I have a question. Previously, we defined the optimal control U with X, but since we cannot measure the true state X, then for the optimal control, which sense does it make in real life to define it as
U
minus X
yeah,
KX
that's a very good
as before?
question. Yeah, no, very good question. But this one, I'll wait until the end of the lecture to answer because there'll be a slide just on this topic. Okay, so if you allow me, I will just wait until the end of the lecture.
Oh,
but
okay,
yeah,
sure.
good.
Thank you.
Yeah, good observation. It is true that since we don't have X right now, until we learn how it's done, we somehow lost the idea of optimality. Yeah, it's true. Very good observation. Any other questions? Okay, all right. If something like of this nature would be difficult to understand somewhere later, please interrupt me and we will go back or something and discuss it. This is a conceptually difficult part. It's not difficult as in mathematically, it's just conceptually difficult part. It would be worth our while to go back. So please, at any time, ask me to go back. Okay. Now, here we have, just to reiterate, X and Y are the state and the output of the system. We can call it true or actual output, right? So it is something that is related to the real world. True output, actual output. Okay. And then separately, we define X hat. It is estimated state. And similarly, we can define C times X hat equals to Y hat. That will be estimated output. Now, estimated output may sound a little bit strange, but basically it is quite straightforward. Since we know how Y is related to X, right? We know there's a formula. So multiply X by C, you get Y, right? If we knew X, we could easily compute Y. The problem is that we just don't know X. But yeah. So we can do exact same with X hat multiplied by C, and we get Y hat. What is Y hat? So like, why do we need it? Well, we actually do need it. It would be a way to compare our estimation with our measurements, right? Because we cannot compare X to X hat, but we can compare Y to Y hat. But okay, we'll do it in just a couple slides. Okay, final observation. We never know the true state X, but we always have available to us estimated state X hat. So the control always relies on the estimated state. That is the situation. That is the situation. Okay. Now let's move on. So let us try to understand the error of the estimation. The error of the estimation. So we can compute it directly as X hat minus X, and we can call it epsilon. Right? So X hat minus X is epsilon, is error. If we want it to be 0, the only problem is it is not quite clear how we can compute it, right? Because we don't know X. Since we don't know X, we cannot compute epsilon. All right. So as a second best option, since we cannot compute this guy, we can compute the error, the estimation output error, right? So what we can do is we can get our estimated output, Y hat equals to C X hat, and we can compute our estimation error as estimation output error as Y tilde equals to Y hat minus Y. But just to avoid too much notation, instead of Y hat, we simply put CX hat, right? So again, the CX hat minus Y. Now let us dwell for just a second on the equation 4. What we have in the equation 4 is the equation where each component is available to us, to our microcontroller, directly. So let me just go over it. So C is a model parameter. Okay, we know it. X hat is estimation. it exists in the memory of the microcontroller. So we do know it. We do not need to worry about where we get it. It exists in the memory of microcontroller. Y is available to us through sensors. So it is sent to the port of the microcontroller by our digital sensors, most likely, right? So again, it is available. So in fact, this Y tilde is directly available to us. There is no problem of where to find it, how to compute it. It is available. Whereas epsilon is not available. We cannot compute epsilon, but we can compute Y tilde. Again, just important fact. Important fact. Let us keep it in mind. All right. Next. Next, what we can do is consider again, one more time, our favorite system, x dot equals to ax plus bu, with the measurement y equals to cx. Okay. We want now to come up with a way to estimate x. It is not quite clear so far how to do it. We can try to, come up with all kinds of algorithms and other things like that. But I will just present you one approach, one of the many, but one approach. Okay. So here's my proposal, how we can start. The proposal is that the dynamics should also hold for the estimate, right? So let me explain it. Like the dynamics holds for x, right? Well, same dynamics should hold for x hat, right? Some x hat somehow should also behave the same way as x. So let us just say that x hat dot is equal to a times x hat plus b times u. That is perfectly legitimate because here we have x hat, that is a known entity. U is also known entity, right? U, we get it from as minus k times x hat, so we know what u is. So expression 6 contains only known variables, and we can use it. We can use it for estimating x. Okay, all right. Now we have to make a few observations about that. If we knew initial conditions of our original system exactly, then what we could do is we could find the exact same evolution of x hat as x, right? Because if they matched initial conditions, they would behave absolutely the same, mathematically speaking. So they will behave exactly the same as long as the initial conditions match. Of course, in practice, and by the way, no need for measurements. Notice there is no need to measure anything here. Like this guy does not use y at all. So somehow it sounds too good to be true, and it is. It is too good to be true. It's not going to work. We don't know initial conditions exactly, and there are other reasons why this wouldn't be a good idea. Other reasons why it wouldn't be a good idea. But for now, let's just say that initial conditions we don't know. Okay. We can call it open loop observation. Why open loop? Well, because we don't have any corrective term here. Basically, we say, okay, we start from some initial value, and then we just go on and on somewhere. There is no corrective, right? We don't use the feedback information from the actual model. So we call it open loop. All right. So this is not going to work very well, but the idea is, attractive. It looks correct somehow. So now what we need is to modify this idea to make it even better, How do we do that? Well, the way we do it is by introducing an observer. That is the title of the lecture, observer. So to make an observer, what we do is we add a corrective term. You maybe, you definitely remember corrective term in control. That was u equals minus kx, right? We could use it to make unstable dynamic stable. Now, corrective term in observers would be given as minus L y tilde, minus L y tilde. Okay. So the idea is that this is a corrective term that would use the information about how different our observations are from what we expect to steer the observer into the correct direction. So for example, we start to diverge from the true state, like the true state goes like this, we go like this. The observers do diverge, we correct to go back to the true state. All right. Now, here we remember that y tilde is equal to cx hat minus y, right? Cx hat minus y, that is y tilde. So our corrective term appears as y minus cx hat. The minus sign, let me just notice, this minus sign is being absorbed in the difference in positions of those two guys, right? Those two guys changed their positions. There's where the minus sign went. Okay. And that's what we got. That's what we got. So let us look into it element by element. We get x tilde dot, oh sorry, x hat dot. So the derivative of the x hat equal to ax hat plus bu plus the corrective term, where we have L, that is observer gain, times the difference between expected output and actual output. Here's the actual output minus expected output. Okay. So together, all of this is x tilde, but it is like our output minus what we expected to see as an output. That is the situation. That is the situation. This is called the Luenberger observer. Luenberger observer. The idea of a Luenberger observer is this. We take our original dynamics and we add to it a corrective term based entirely on the output. We compare the expected output with an actual output. That is the whole idea of Luenberger observer. So original dynamics, but written in terms of estimates, plus corrective term. That's the Luenberger observer. Do we have questions about this so far? Okay. Now, big task. How do we find observer gain L? Observer gain L is a good question. It's a good question. Okay. All right. So what we want to do first is to take this guy and subtract from it our original dynamics. That is a very standard idea in control. We'll find this type of difference because it would give us error dynamic. In this case, it is called observer error dynamics. Right? How would it look like? Well, we would have, yes, let me just use color coding. So we have this our color code in red. This our color code in green. So we have our observer components, right? Minus our original dynamic components. Notice that this part was cancelled with this part, right? Because they're the same. Control cancelled. Classical situation, very typical. Okay. Now what we have next is we can isolate here x hat minus x. And here what we can do is isolate L cx hat minus cx. Where does this come from? Well, y is cx, right? Okay, so that's it. The way one more time I replace the order of those terms and we put the minus sign in front. So basically we went back to this formulation. Okay. Now here's the situation. We know that x hat minus x is epsilon. X hat minus x dot is epsilon dot. Here is the same thing. We get LC times epsilon. So LC times epsilon. So ultimately what we obtained is the following. We obtained a closed loop formulation. That is what we can call it closed loop formulation. In terms of epsilon. So the difference between this guy and this guy gave us this new dynamical system 10. This dynamical system 10 explains to us how the error in estimation of x behave as a dynamical system in its own right. We cannot simulate it forward because we don't know initial conditions, but we know its stability properties, which would clearly depend on A and LC. So without saying anything about x or x hat, we can already say that this system will be stable or unstable depending on A minus LC eigenvalues, right? That is a big step forward, Okay, so this guy will be stable if this matrix is Hurwitz. Remember, real parts of the eigenvalues have to be negative. Okay. Now, all we need to do is to find such L that would make A minus LC stable, so Hurwitz. Can we do it easily? Well, not quite. Let us see, remember how we did it with K. With K, we had A minus BK have to be Hurwitz. A minus BK. K is on the right side of B. What we have here is we want to find L, such as L minus LC is Hurwitz. Well, notice that L is on the left hand side of C. So somehow we deal with a situation where we do not have an ability to apply our previously designed method for the same task because L is on the wrong side of the matrix, right? So something doesn't match up here. We would have to develop new methods, it seems, for this task. Okay. Seems to be a problem. Seems to be a problem. Okay, let us try to solve this problem. Well, we use the first mathematical fact of the day, and that is if this matrix is Hurwitz, then this matrix has to be Hurwitz, and vice versa. So if the matrix is has like negative real parts of eigenvalues, its transpose would also have negative eigenvalues with negative real parts. In fact, eigenvalues of the matrix are equal to eigenvalues of the transpose of the matrix. Transpose preserves eigenvalues, not eigenvectors, eigenvalues. Okay. This fact is not completely obvious, and the proof of it will be in the appendix. I'm not sure if we want to go through it in the class. If I have time at the end, I will go through it, but I don't think we'll have time. Okay, but at the end of the slides, you can see the proof, and I recommend you go through it. It will be interesting. Okay, so we have this situation where the eigenvalues of the transpose are the same as the eigenvalues of the original matrix. So we can try to find such L that A transpose minus C transpose L transpose is Hurwitz. But that problem is exactly same type as control design, because now L transpose is on the right side of C, exactly like K was. So now we can just solve it using Riccati equation. So I can write it out, the solution, in such a way. L transpose can be found as solving LQR for A transpose, C transpose, Q, and R. Q and R are our cost matrices. Okay. Now, we could do it as a pole placement. It would be something like this. L is equal to place. I'm not sure how we call pole placements in Python, but let's say place. L transpose, A transpose, sorry, C transpose, P, where P are desired eigenvalues. Yep, that's it. So the trick was to, instead of designing L for the original problem, to transpose the problem and design L for the transpose, for the dual problem. Okay. So that is the way to do it. That is the way to do it. Do you have questions about this part? Okay. So now we solved the problem of how to design a observer gains, which would make sure that X estimation error in X goes to 0. So let me notice, we're not talking about estimation error in Y, like the difference between outputs, Y tilde. Y tilde is going to go to 0 for sure, because Y tilde is just C times epsilon. But what is going to go to 0 is epsilon itself. So the difference between actual state and the measured state, sorry, and the estimated state. So our observer is going to behave really well, exactly like we want. Sounds very good. Sounds very good. Okay. Let's see if we have any problems, if there is anything left to think about. Well, let us just combine it all together and see what's going on. So here is our original dynamics. X dot equals to AX plus BU. There's our measurements, y equals to cx. Here is our observer, x hat dot equals to ax hat plus bu plus L times the difference between outputs, right? And we have our controller u minus equals to minus kx hat. Right. That is everything put together. Now this is our new system, where we know that A minus BK is Hurwitz, and A transpose minus CL transpose is Hurwitz. Okay. Now I will rewrite this dynamics in this way. So instead of U, I will substitute minus K x hat. So we get this term minus BK x hat. And here we get this term minus BKX hat. Okay. And instead of y, I will substitute cx. So we would get LCX minus LCX hat. All right, so equation 12 now is this new system of differential equations. Now here's the question. Here's the question. Can we claim that it is stable? Can we claim that it is stable? So far, I don't see how we can do it. Indeed, the observer itself is stable in terms of observation error. Observation error is going to go to 0. That is true. But does it mean that the system itself is going to be stable? So the combination of the robot plus the observer, will they behave stable? Basically, the only thing that can be unstable is if the robot itself starts to misbehave, right? Like imagine you have a quadrotor, you plug in the observer and starts to lose control, degenerate into instability. Can it happen? Sure, why not? You have to prove that it won't happen. Otherwise, you have to guess, and we don't want to guess. So while observer will try to catch up to real state of the system, the real state can be unstable, right? So we have to somehow prove that it is stable, like after we plugged in the observer. Okay. Now let's move forward. Okay, I will now rewrite this whole thing as a matrix. I will rewrite it as a matrix. So we start by noting that x dot depends on a times x, right? So the connection between the way to think about rewriting the systems as a matrix is this. You have two variables, right? Two decision variables, x hat, x hat. Then you have two equations. So two outputs, in this case, x dot and x hat dot. You have to decide how each of those equations, each of those like x dots, depend on each of the variables. So the relation between x dot and x is just a. That is the only relation we have here. The relation between x hat and x dot is just minus bk. So that's the only one. The relation between x hat dot and x is only LC. So only LC. And finally, the relation between x hat dot and x hat is a minus bk minus LC. So this guy. Okay. Well, that's how you construct it. Now let us look at what we got. This matrix here, it has to be Hurwitz for the system to be stable. That is the method we know. Like we want this matrix to be Hurwitz. If it is Hurwitz, the whole thing will be stable. But do we know that it is Hurwitz? We don't. Like there is just it's unclear. It's unclear. So we want to somehow be able to talk about eigenvalues of this matrix. And so far we cannot. But there is a way. There is a way to do it. So let me show you how it's done. And what I'm showing right now is not just derivation of a theorem. It is a practical method which can be used for working with a class of systems well beyond observer. So is consider the derivation as part of the material is very useful in practice. Okay, so let's look into it.
Oh, excuse me, may I ask a question?
Yeah, go ahead.
Why can't we find the eigenvalues of this matrix?
We can compute it in like if you give me like one like particular matrix like this, right? You give me just a matrix with particular values like A is equal to this, B equal to this, K equal to this, etc. I can compute eigenvalues, no problem. What I want to do though is to prove that the way we designed controller and observer, the way we designed them previously, would guarantee stability. Because otherwise, if we have to first design controller and observer, and then compute eigenvalues of this matrix, we are basically putting ourselves in a situation where we first design something, and then we check if our design is correct. Instead, what we want is to prove that our design will be correct beforehand. We don't want trial and error. So while computing eigenvalues of 14 matrix 14 is both possible and a good practice, like it is a good idea to always do it numerically, what I'm trying to do right now is to get towards a theorem which would allow us to maintain our design methods from previous two lectures. That's it. I'm not saying that we cannot compute eigenvalues. I'm just saying that it is like looking at the matrix 14, I cannot tell you any properties of the eigenvalues. That is all that I'm trying to say. Okay.
But is there a global task to find such B and L that will make our matrix, our system stable?
K and L, yes, we want to find K and L that would make the system stable. Is correct.
Okay, thank you.
Mm-hmm. I hope this part will become clearer in just two slides. In just 2 slides, it will become clear. Okay, so matrix 14. So what we want to do with it is introduce a change of variables. We introduce E as x minus x hat. You notice that E is actually just a epsilon backwards. It's minus epsilon. But it is, that is how we do this derivation. So I introduced new variable. I hope you forgive me. I could have used minus epsilon here. Okay, so E equals to x minus x hat. This implies that x hat is equal to x minus E. That is important. It's trivial, but it is important to keep in mind. So the way we defined E here gives us x hat as x minus E. Okay. So in other words, E is the difference between true state and estimated state, but estimated state itself is the difference between true state and estimation error. Okay. So this is what we had last on the last slide. I think expression 15 is what we had on the last slide. Now, what we can do is we can find a difference between x and x hat to get E, right? That comes from the definition. So E dot equals to x dot minus x hat dot. So what we would get is this guy minus this guy. So we can this guy minus that. Okay, all right. What we can observe here is that some parts cancel out instantly. Like as before, this guy will cancel with this guy. We can observe that some parts we can get A out of the brackets, like here. And as before, again, we can observe that here we can get LC out of the brackets. So what we get as a result is very similar to what we saw previously. E dot equals to A minus LC E. Okay. And we know that this guy is stable because A minus LC is stable. That is, we established it in the control design. We designed controller in such a way, observer in such a way that A minus LC is stable, is Hurwitz. Okay, but this is only part of the problem. Now, let us rewrite this guy, take into account that x hat is equal to x minus E. Right? So what we have is x equal to A minus bkx. Where did bkx come from? Well, it is bkx comes from here, because this becomes minus bkx plus bke, right? And here's bke. So again, this guy becomes now this guy. So because of the way we introduced our new variables, what we got is A minus bkx plus bke, that is equal to x dot. So we simply rewrote our two equations in terms of new variables. Now our two equations is E dot equals to A minus LC, and x dot equals to A minus bkx plus bke. Now let us write it as a system. And we have here x dot equals to A minus bkx plus bke, and E dot equals to A minus LCE. In terms of matrix, of course, we write like this, right? This is a block how x dot it depends on x. This is a block how x dot it depends on E. This is a block how E dot depends on E. All right, quite clear. Now comes interesting part. For block triangular matrices, it is true that eigenvalues of the entire matrix are equal to combination of, sorry, how should I put it? Include eigenvalues of the blocks on the diagonal and nothing else. So the set of eigenvalues of the entire matrix is just a direct sum of the eigenvalues for each of the diagonal blocks. So basically, all we need is to find eigenvalues of this matrix and find eigenvalues of this matrix. And together, they represent the eigenvalues of the entire matrix, okay? So together, they represent the eigenvalues of the closed loop system. But that means that the system is stable because we designed controller in such a way that A minus BK is stable. And we design observer in such a way that A minus LC is stable. Okay. So that is the achievement. So the reason for our change of variable here was just to change this matrix, which had no structure, to this matrix, which had a upper block block diagonal structure, upper block triangular structure. Okay, so it had blocks on the diagonal and above, but no blocks here, no block here. And we use this property. By the way, proof of the property is appendix B. Interesting proof. And yeah, together we have this situation, right? Let's look at this for a second if you have any questions. Okay. Now, what this result told us is we could design A minus BK and A minus LC separately. And as long as they're designed to be stable, so as long as the observer is stable and the controller is stable, the overall system is also stable. This is called a separation principle. In fact, it is not just a principle about stability. It is a principle about eigenvalues. So eigenvalues of the entire system are just eigenvalues of those two individual components. Of course, here I would like to notice that we're talking about eigenvalues in terms of variables x, which is what we care about, and e, which is observation error. So not about x hat. If we want eigenvalues in terms of x hat, we have to think about it, right? This is in terms of e. But if e goes to 0, x hat definitely goes to x, right? So there is no problem here. And x itself goes to 0 simply from equation 17. Right? And if x goes to 0 and e goes to 0, x hat has to go to 0 because x hat is the difference between those two. So here's how we proved stability of the overall system. And in a sense, we can talk a little bit about optimality. So what you asked me before was how does optimality work here? What I can say is this. If our optimality can be expressed in terms of eigenvalues that we obtain, so for example, we get our optimal controller, LQR controller, and gives us controller gain K, which is optimal in terms of the cost function, right? And we get the performance of the system expressed in terms of eigenvalues of the system. All those eigenvalues are preserved here. So even as we use our controller not as minus kx, but as minus kx hat, right? This is our controller. Remember, like this is our controller. Even so, we still get our eigenvalues in terms of x the same as we got them at the design stage. So eigenvalues of the x coordinates are preserved. Right? Same about the observer. So as long as you're willing to think about optimality in these terms, as we designed the system for just a controller without regard for observer, and we get optimal controller gain, which gives us some eigenvalues. Well, those eigenvalues will be preserved. If you want something else, not just eigenvalues, like you care about some other performance matrix, then we have to rethink optimality. And in practice, there is a lot of aspects of optimality that we have not yet looked at, right? We only looked at like the cost in terms of X and U. If you want, you can try to include everything in your cost and try to solve this more complicated Riccati equation, which would at the same time design your observer, controller, and the cost would include everything. Then there wouldn't be any question of preserving something because you would directly use the results in practice, right? Like there wouldn't be this strange step where you design something for u equals to minus kx and then use it for kx hat. This is a strange step, right? This is a strange step. And you can avoid it if you simply use one optimal control design for the whole system. Okay, and this can be done. This can be done. We usually don't do it directly from Hamilton-Jacobi-Bellman. Instead, there are optimal control techniques, especially in LMI control, which they do it a little bit differently. I think it's outside of the scope of the course, so you would have to study it on your own or just wait for courses on optimal control, maybe late in human studies. But those things can be done. But ultimately, at least you can see that eigenvalues are preserved. And in practice, that might be exactly what you want. If you care about how oscillatory your system is, how fast it decays, that is eigenvalue stuff, and eigenvalues are preserved. So in fact, in some sense, your optimal control design is, in some sense, is preserved through this process of doing it with the observer. And the observer is done in the same way, by the way, right? You design your observer, again solving the Riccati equation. But for it, you remember we preserve the eigenvalues, but only in terms of the observation error, not in terms of x hat, but in terms of observation error, E. So slightly different stuff. Right, so that is the idea. Well, this is called separation principle. I would recommend you to remember the name. It's important because it holds for linear systems and it is very powerful. It doesn't have to hold for every system you encounter. So if you want to use it outside of linear system, make sure you check if it actually holds. It doesn't have to, right? We only managed to prove it for linear systems. All right, how much time do we have? Are we out of time? We are out of time, right? Yeah. All right. Again, I would recommend you to just check the proof of two mathematical facts we used. Eigenvalues of the matrix equal to eigenvalues of the transpose. Right? In short, the proof, the idea of the proof is you write a determinant equal to zero equation. Determinant itself is a scalar. You can transpose it without changing it. And determinant of A is equal to determinant of its transpose, right? So you have this thing. And then you notice that this matrix has what we call null space. So since its determinant is equal to zero, so there would have to be a vector which would be multiplied by this matrix that would send it to zero. And that is the proof. That is the proof that this is eigenvalue of n. For block diagonal matrices, slightly more complicated. You basically get eigenvector for A and for C, right? The first proof that eigenvalue for A would also be eigenvalue for the whole matrix is quite simple, because you basically say, okay, the eigenvector for A matrix plus zero block, if you multiply the whole matrix by it, you get this guy, which is just V times lambda, right? It's quite simple. For the second part, it is more complicated because we multiply by eigenvector this whole block here. Just follow the derivation. It is nice, and those derivations, I include them because the techniques here are kind of the same as you use in like dozens of areas. So it's like a lot of those ideas are very standard in linear algebra. So just check it out. Right, that is it. I will stop the recording and we see if we have any questions.